This video shows how to derive the Taylor series for complex analytic functions. Spoiler alert, complex analytic functions have the same formula for their Taylor series as do real functions, but the derivation is a little bit nicer because it makes use of the better structure that analytic functions have. We'll be finding a power series for an arbitrary function that's analytic, and I'm going to, without loss of generality, find the power series centered at the origin, z equals 0. If you want a power series centered somewhere else, it's very easy to just pick up and translate the function. So I'm going to, without loss of generality, just focus on functions that are analytic at the origin. So here's the goal. The goal is for a function f, which is f of z, analytic at z equals 0, find a power series representation. And the observation is for all z in some open neighborhood of z equals 0. In order to do that, well, the function is analytic at some neighborhood of z equals 0. That means there's an open set, and that's pretty decent. And the other thing to really notice is that analyticity is going to give us this equal sign here. The normal Taylor's theorem says that, yeah, it converges, it's equal under certain conditions, blah, blah, blah. We get just an outright equal sign here. My comment about the centering, if that bothers you, that's centered at z equals 0. And so you can move that around to any other point by moving around the neighborhoods and where f is analytic. Of course, the thing to realize is whenever I have a function that's analytic somewhere, then I have the Cauchy integral formula. And what does the Cauchy integral formula tell us? It tells us about, I've got my point where the function is analytic, I've got my z somewhere nearby, and I have some region on which f is analytic, so that analyticity is happening in that region. Since it's an open set, what I'm going to end up doing is I'm going to end up centering not only this point z, or this region, but also I'm going to center a circle. I'm going to center a circle, I'm going to traverse it counterclockwise, c. And the reason for doing this is because I want to use the well-regarded and very useful Cauchy integral formula. Cauchy integral formula says if I have f being analytic on some simply connected region D, bounded by a simple closed curve C, traversed counterclockwise, like for instance this circle here, then I can actually have a formula that tells me what all the values of f are in that region. So pick that point Z, somewhere in there, and you want to know what value f has on Z, use this formula. Now that's the lesson. So we're going to make use of a geometric series. If we're going to use a geometric series, we're going to want to know about its convergence. We want to make sure it converges. And the thing to notice is that this Cauchy integral formula involves this variable s. There's the s. It's the variable of integration. So s lies somewhere on that curve, somewhere on that circle. You will notice that if I compare the distance of s to the origin and z to the origin, well, z may be distance 0 from the origin, but in any case, s is further. So if I take a look at this and take a look at the ratio z divided by s, that's less than 1. The reason why that's important is, well, you'll see in a moment, it's important because it tells me about geometric series convergence, because the geometric series convergence has got a r less than 1 kind of property there. That's kind of what we're going to be after. All right, so to that end, let's start our derivation. We're going to start our derivation right on the Cauchy integral formula. So let me just copy it over here and move along to a new page. All right, there it is. So I'm going to do a little algebraic trick, and that algebraic trick is going to expose to us the geometric series we want. You factor out an s from the denominator. If I do that, I'll get a 1 here and a z over s here. This latter thing right here looks an awful lot like a geometric series in disguise, and in fact, provided the magnitude of z over s is less than 1, it's actually equal. So, the thing to notice is if magnitude of z over s is less than 1, then 1 over 1 minus z over s is equal to the sum, and equals 0 to infinity, z over s to the n. And we know that that actually is the case because of this geometric picture right here. Great. Okay, so given that's the case, I can actually just write outright equals right here. And drop right in this sum. Nice. Fair enough. Let's do a little bit of algebraic manipulation. You'll notice the z to the n's there, they're all constants as far as the integral is concerned. The s's are not. So, because of all the convergence we got going on here, I can think about integrating term by term and switch the integral and the sum. So there I've just switched the integral and the sum. Let me go a little further. Let me pull that sum all the way out, because remember we're after a power series after all. And we're even after a z to the n. There's our z to the n. That guy's a constant as far as the integral is concerned. Don't forget my 1 over 2 pi I. There's the integral, and what does the integral become? Okay. Now, here's something a little funny. We started out with the Cauchy integral formula, right? Right there. There it is. But we can tell, what is this quantity? This quantity in the parentheses, again, Cauchy integral formula. Again, this is actually almost the derivative. This is almost how many derivatives? Well, it's n plus 1 derivatives of f evaluated at 0. This is the Cauchy integral formula. Again. Cool. Why do I say almost? Well, because when you take lots of derivatives, you end up with factorials. So let's fix that. All right. Let's put in our n factorial thingy here. And you will notice that, well, it's not quite n factorial there because it's compensating for that. So what we really should do is go divide by, and then all is well. Alright, that's what that is. Great. So, putting all these pieces together, we get something that looks like 1 over n factorial, f n derivatives at 0, z to the n. And oh gosh, that's the usual Taylor's formula. Usual is spelled wrong because, just because. Let's fix that. And you will notice really the only place where we need to do any kind of justification, and if you're interested in that justification, I have another video about that. This is the term by term integration convergence. So that's the only place where we need to sort of watch out a little bit. The great thing with analytic functions is this term-by-term integration just works. So that's pretty nice. And so you end up with finding Taylor's theorem just works for analytic functions. Consequence which is surprising. I didn't really need to assume much about f, did I? Well, actually, I did. F was analytic. That's a big assumption. So, in consequence, there's a very important corollary. All analytic functions are equal to their Taylor series. And of course, caveat is where they are analytic after all. That means you can go ahead and compute all sorts of neat things about analytic functions by doing power series manipulations, or you can go the other way. And they're really actually one and the same. This is actually kind of useful from a terminology standpoint. That being, when we say analytic, oops, I mean that, means equal to its Taylor series, as opposed to holomorphic means satisfies Cauchy-Riemann equations. And the point is, for real numbers, of course, Cauchy-Riemann equations have nothing to do with anything because there's all those i's floating around. But they are the same. These are the same concept for complex functions. And really the only thing that works in R is analyticity. So you can have real analytic functions, you can have complex analytic functions, but complex analytic functions additionally are holomorphic, and those are equivalent. So that's pretty neat, and that gives you a lot of power. And that's really what wonderful things that come out of complex analyticity really are pretty much statements about power series as well.